So this section is on the Moon and Mercury, the cratered worlds. We know Moon's not a planet, but it's a big object compared to some of the smaller planets. And it has some similarities to Mercury. So here's a picture of Buzz Aldrin on the Moon. The footprints that you see in this image will probably last millions of years. There's a lot of interesting stuff going on in that. You can see the very dark sky in the background. This is a daylit object, and so it's very bright on the Moon when you're in the daylight. You can see the American flag, which is not flapping in the breeze. I don't know if you can see it's got a rod across the top, so it's hanging almost like a curtain. It's made out of crinkly material, so it's just like that. It's not flapping. Some data on the Moon. That shouldn't say Neil Armstrong. That should say Moon data. We'll fix that. The Moon has no atmosphere, no liquid water, no magnetic field. It's got a small core. The Moon has been geologically dead for about 3 billion years. So there's really nothing going on. Oh, there are tiny earthquakes on it and stuff like that occasionally. So it's got something going on way down deep inside. But its lithosphere is very, very thick. We'll later discuss some hypotheses about how the Moon is formed. Those are pretty well agreed upon. Look at the temperatures, 266 degrees Fahrenheit in the day, minus 292 at night. It's about the same distance from the sun as the Earth is. And yet look at the difference. We don't get anywhere near that cold or anywhere near that hot, anywhere on the planet. And the reason is because we have an atmosphere. And so that's the effect of not having an atmosphere. You might occasionally get up into the mountains and realize that it cools off a whole lot at night if you're up in the mountains at high elevation where the air is thin and the heat can escape easily. The Moon has about a 7-degree tilt in the orbital plane relative to the ecliptic. Remember, the ecliptic is the plane of the Earth's orbit around the sun, and the Moon's orbit is not in that plane. And so that's interesting. There's some interesting stuff, consequences for that, about how the Moon formed or how we got the Moon. We have a big moon, and none of the other small planets have big moons. There are only 7 big moons in the solar system. Jupiter has 4, Saturn has 1, Neptune has 1, and Earth has 1. The Moon's mass, as big as it is only about 1.25% of the Earth's mass. The Earth and the Moon rotate about a common point called their center of mass. Like, if you throw a hammer, it'll tumble about its center of mass, which is somewhere near the head of the hammer. The center mass of the Earth-Moon system is located inside the Earth somewhere off-center. The Moon's about 2,200 miles in diameter. It's a little smaller than with the United States, about a quarter of the diameter of the Earth. The Moon undergoes 1 rotation per revolution. This is called synchronous rotation. It always keeps one face towards the Earth. We talked about this in the last section where we talked about the Moon. The Moon's orbit is slightly elliptical. It makes it appear to wobble slightly from our perspective, but you wouldn't notice it unless you saw like a time-lapse photo of it. It's very close to circular. This is why you'll sometimes hear them talk about a supermoon, because it's, if the orbit's elliptical, it's a little closer sometimes, a little farther away. The Moon's, the whole area of the Moon only changes by about 5%. So if you ever hear anybody saying that it's going to be 10 times as big, it's nonsense. Most of the stuff about that is nonsense. A supermoon is it's like comparing a 16-inch pizza to a 15-inch pizza or something like that. It's hardly noticeable. So since the Moon always has one face towards us, that's what you're seeing on the left in this picture. And on the right is the backside of the Moon, which was first seen by the Apollo astronauts, and as far as I know, only seen by the Apollo astronauts, since nobody's been around the Moon since then. So there are dark regions over here called mare, or Maria is the plural. It means sea in Latin, I think. And you can see that they're kind of round. Hopefully you can notice that these are just little round patches. They're volcanic plains that are a result of big impacts at the end of the cratering era. On the right is mostly this white stuff, which you see around here on the left side too. That's called terrae, which stands for terraces, or which means terraces, because they're higher. The terraces are older. They're more heavily cratered, and that means they're older. And they're higher. They're like a mile or 2 higher in elevation on average than the mare, the dark areas. So here's a nice picture of the terrae. They formed about 4.1 to 4.4 billion years ago. Um, uh, we can tell that a couple of ways. We can do radiometric dating on it by sending guys up to the moon in the 60s and 70s of the last century and bringing back rocks and radiometrically dating the rocks. And we can also tell it by the density of craters. That gives us some clues about how old that surface is. And so it's pretty cool that we can use cratering rates to determine ages, because we can use it on other moons too that aren't ours, like Jupiter's moons or the surface of Mercury and stuff like that. The Terrae occupy about 85% of the surface of the moon. They're a few miles higher in elevation than the Maria, which are formed about 3.1 to 3.9 billion years ago. So they're also pretty old, but they're not as old as the Terrae. If you look at the Maria, maybe we have a picture here, you can see that there's many fewer craters. They kind of formed right at the end of the big impacts of the cratering era, and so they don't have nearly as many craters as the Terrae do, which means they were erased. They still got the craters here, but some kind of volcanic activity happened and cleared them out. And so these are younger areas. Large impacts sometimes triggered volcanic eruptions, which caused these plains to be formed out of a slightly different material, a darker material. The lunar magma was darker than the crust. Okay, Mare is like Latin for sea, I think is what it stands for. So here's a particularly large crater on the moon, a prominent one anyway. It's about 50 miles across and about 3 miles deep. It's named after Tycho Brahe. We talked about him before. He's the Danish astronomer who measured the positions of the planets, and that Kepler used that data to deduce the correct laws of planetary motion. Crater Tycho is a nice example of a crater with a recoil peak. You see this peak in the center. When people were looking at pictures of the moon, looking at the moon through a telescope years ago, they didn't know if those little circles there were craters or volcanoes. And as they started looking at them, they started seeing these peaks in them. And volcanoes don't have that. That's an impact phenomenon. There's a recoil when you have an impact like that. There's a recoil. If you get liquefaction, which you do, these things that make these holes are going like 10 miles a second, and they're big. And so if you drop something into water, you'll see some water splash up out of the center. And so that's a phenomenon that's understood. Here's a zoom in of the recoil peak of the Tycho crater. It says it's 2 kilometers above the floor, so that's about a little over a mile above the floor. Tycho is about 50 miles in diameter, so these guys are probably 5 miles across, and that was a pretty big impact that made that. Here's a footprints in the dust. Lunar soil is called regolith, which literally stands for blanket of stone, or means blanket of stone. It covers the lunar surface. It's soft like talc. It's a fine powder, and it's like that all over the planet because it's had billions of years of being bombarded by meteorites, just microscopic ones. The things we call shooting stars burn up in our atmosphere, but on the moon they hit the surface, and so they just sandblast the surface constantly. It's declined over the last 4 billion years, but every spot's been hit, and so they get this fine powder. There was some concern about whether humans would be able to walk on it, would be able to land a spaceship on it, but they tested it before the Apollo guys went there. They landed a couple of spaceships on it first to make sure they would hold them up. Here's just some contrast to whether they were craters or volcanoes. So on the right is what a crater would look like, and on the left is what a terrestrial volcano would look like. There was some concern that all of the craters are round, and they thought, well, if there was a low angle impact, like coming in here at a funny angle like this, which a lot of them should, craters should, meteorites should come from every direction, right? That you should get a streak rather than a circle. But it turns out when they're going really fast, even at very low angles, you still just get a round hole. there, and they tested that ballistically on the Earth. So high-speed impactors create round holes regardless of the impact angle, and they create these recoil peaks. And so pretty much everything we see on the moon is a crater, all around things. So this is how craters form. An object comes in, it makes an impact, makes a big hole, and then you get a pile of mess with a recoil peak in it. And so the speed of the impactor is around 10 miles a second. Typically, the diameter of the crater is about 20 times the diameter of the impactor. So if you have a impactor that's a mile across, you're going to have a hole that's 20 miles across. So that's a big hole. It blows out. The projectile vaporizes, and shock waves spread through the lunar rock. Ejector thrown out of the crater. Recoil peak is left behind. By the way, sometimes these will blow stuff out and escape the moon and come to the Earth. And astronomers and astrogeologists can identify moon rocks on Earth. We can also identify Mars rocks on Earth. Their chemistry is slightly different, and they can actually find rocks that were blown off the moon or off of Mars and somehow landed on the Earth. We get craters on the Earth, of course. This is Meteor Crater. It used to be called Barringer Crater in Arizona. I don't know when this one happened. I should know. I want to say it's like 30,000 years ago, but I'm not positive. The meteor was estimated to have about 60 meters in size. It's about 1.2 kilometers across, a little more than half a mile across. It's about a factor of 20. Maybe you visited that. Oops. Okay. So here are a couple of views of the moon. You can take a global view of the moon. This is how we see it at different times. On the right is a full moon. On the left is maybe a little past first quarter. There are a couple of things to notice. First, once again, you can see the mare on the right, and you can see them on the left too. These are slightly different exposures. And by the way, this is the crater Tycho down here, and so it's here and it's here, right? And so you can see it in both of them, and you can see the blast. Tycho is a very recent crater. That is to say, it's about 100 million years old, but most of the big craters there are billions of years old. So it's recent. There are a couple of things to notice. First of all, this line between light and dark on the left here is called the terminator, right? It's where the shadow starts. And if you're standing on that spot, what time of day is it? Can you tell me? It's either sunrise or sunset, right? Depending on what the moon, which half you're on, which part you're on. And so you have long shadows. And so you can look at craters along the terminator and see a little more of their structure than you can when they're lit face on to you, right? And so often when we look at the moon, if you're observing the moon, you like to see it when it's not full. Even though when it's full, you can see the whole thing. When it's not full, you can look along the terminator and see some cool stuff. So it turns out as the solar system formed, and we kind of talked a little bit about this, objects got bigger and bigger. They were accreting, kind of snowballing into bigger and bigger objects as the solar system was forming, as the sun was forming. And that resulted in things knocking into each other. And so even after the planets sort of formed, there were still things floating around the solar system that were smashing into planets, and getting pulled in by the planet's gravity. And so we now have some sort of mathematical sense of what these cratering rates were. So this is kind of a graph of it, and we can tell, this is the time before the present. So over here on the right is present time. That's 1 billion years ago, 2 billion years ago, 3 billion years ago, and so on. By the way, this says Tycho at about 1 billion years, and it should be about 100 million, pretty sure. So it's not perfect here, but So you can see the cratering era sort of ends about maybe 4 billion years ago, or a little less than that, a little less than 4 billion years ago, right? Most of the cratering for the highlands happened about 4.3 billion years ago. One of the things scientists can do, which is pretty cool, is they can look at the density of the craters and then tell how old the surface is based on sort of on this curve. Ah. I'm never going to get that right again. All right, how if I do it like that? So, how did the moon form? So there are really 4 hypotheses. 3 of them are wrong, but these have been tossed around. The one that's currently accepted actually came out when I was in college in the early 80s, 1980s, and I heard a talk by one of the guys who was promoting it, and it seemed impossible but interesting, and now it's sort of accepted fact. So the first hypothesis is the fission hypothesis. The moon was forming out of the same material as the Earth and kind of spun off. They were kind of forming together in a big glob of material that was spinning, and the moon came out of that. And it turns out that the moon and the Earth are not made of the same materials. Their chemistry is slightly different. And so that hypothesis fails, because if they formed out of the same goop, they would be made of the same goop, and they're not. And so that was the fission hypothesis. The sister hypothesis says the moon and the Earth formed separately, but adjacent to each other. So they were gravitationally connected already, but they were separate globs of material that were forming into an Earth and a moon. The problem with that one is that the physics of that says that they would have the same angular motion, and they don't. The plane of the moon's motion is not the same as the plane of the Earth's motion. And if they had formed sort of together, even though separately, in the same region, orbiting each other basically, they wouldn't be moving the way they're moving now. It violates the physics. The next one was the capture hypothesis. Well, the moon could have been just off somewhere and got knocked gravitationally around by a bigger planet, and it swooped into the inner solar system the way comets do, and the Earth captured it as it passed. It turns out the physics of this is nearly impossible. Sometimes a planet will catch a small moon. It appears that Mars has done that, but it's extremely rare, and for something as big as the moon, it's just not possible. It's not a reasonable assumption to make. It's not a very good hypothesis, I guess. And so the last one, which is the one that's currently accepted, is called the giant impact hypothesis, and it's currently accepted. And it states that early in the formation of the Earth, the Earth was hit by a Mars-sized object which had formed somewhere else in the solar system, perhaps in the asteroid belt. The collision produced the moon and the Earth and put a tilt in the Earth's axis. Remember, the Earth's axis is about a 23-degree tilt. And it also explains why. So the physics of why they don't have the same rotational motion is reasonable, because this Mars-sized object came in from some other direction and was doing its own thing. And it explains why their chemistry isn't the same. So it's increasingly it's accepted. It also seems to be at least partly responsible why the Earth has all these moving plates on its surface. It got smashed up late in its formation. Its surface did. Let's see. So here's a picture, which I basically stole off the internet. But that's the idea. A Mars-sized object hits the Earth. There's a big impact. There's debris all over the place, and whatever's left of the debris forms into a moon. All right, that's the theory of how the moon came to be. Here's Mercury. Mercury looks like the moon on the outside and kind of the Earth on the inside. It's just covered with craters kind of on the outside, and it's got a giant core on the inside. Its daytime temperature is 662 degrees Fahrenheit, and its nighttime temperature is minus 274. Notice how cold it is at night, even on Mercury, which is a lot closer to the sun than we are. If you don't have an atmosphere, and the sun isn't shining on you, you're going to get cold. It's the second most eccentric orbit of the 8 planets. It should say the most eccentric orbit, the least circular orbit. It has the second most if you're including Pluto. So that should say the most eccentric orbit. Its diameter is about 3,000 miles. So it's about 1/20th the mass of the Earth. Remember, so that's 5% the mass of the Earth. Its diameter is about half again as big as the Moon, and it's about 5 times the Moon's mass, roughly 4 times the Moon's mass, roughly. Its diameter is half again as big as the Moon, and its mass is about 4 times the Moon's mass. It's got about the same density as the Earth. Its interior is very similar to the Earth. Mercury is too small and too hot to hold on to an atmosphere. If you put Mercury way out in the outer solar system where stuff is really cold, it could keep an atmosphere. But it's too hot where it is, given that its small size, to hold on to an atmosphere. So why is Mercury so bright, and why don't we see it? It turns out Mercury is very bright and often gets confused with UFOs. There'll be a bright object on the horizon that appears not to be moving, and people will think it's a UFO or will report it. And so it turns out it's close to the sun, so it's well lit. It's getting a lot of bright light. It gets light about 7 times the intensity the Earth does. It's close to the Earth, which makes it bright to us, right? And so it's both near the Earth and near the sun, kind of like Venus is, right? And so, so the question is, by the way, it doesn't have Venus's albedo. It doesn't reflect 75% of the light. It only reflects about 12% or something like that. But it's so bright. It's easy to naked eye see it. But you have to know where to look. So the question is, why don't we see it? And the answer is because it's so close to the sun. It's never up very long after sunset. It's never high in the night sky. And so it doesn't stand out much. It's always near the horizon. Either the sun is getting ready to come up or the sun has just gone down and it's near the horizon. And so it's hard to see. Mercury is never more than 28 degrees from the sun, so it is up at most 2 hours before sunrise or after sunset. That's not very long. And for a while there, the sky is still pretty bright right after sunset, and so it's still hard to see. By the way, this 28-degree angle is called, the maximum angle it is from the sun is called the angle of maximum elongation. Mercury's orbit. Mercury orbits the sun in 88 Earth days and has a 58 days and 15 hours day, if you know what I mean. Its day lasts 58 Earth days and 15 hours. So it turns once on its axis about every 58.6 Earth days. So its year is 88 Earth days. Its day is about 58.6 Earth days. So there's about a 3-to-2 ratio between its orbit and its rotational period. That is to say, the time it takes to do a year and the time it takes to do a day. Here's a picture of its core. It's got a giant core like the Earth. The Moon has a tiny core. I should have put a picture of the Moon's core in. The Moon and Mercury look nothing alike on the inside. Mercury looks a whole lot more Earth-like than the Moon is. The topography of Mercury's northern hemisphere is mapped in great detail by the MESSENGER data. MESSENGER is one of the spacecraft that went to Mercury. The lowest regions are shown in purple and blue, and you can see it's got a lot of action going on its surface. The difference in elevation between the lowest and highest regions is about 6 miles or something like that. Permanently shallow low-lying craters near the North Pole contain radar-bright water ice. So there's water on Mercury, as hot as it is, but it's near the North Pole, down in these craters, and they don't ever see any sunlight. So they'll never get that 600 degrees Fahrenheit stuff. Here's a little interesting thing about Mercury. We had to measure its rotation rate with radar because it's too low in the sky to get a good telescope on it. At least back in the day it was. Now we have probes that can do that, but spaceships that can do that. But early on we had to measure it with radar. And what you do is you send a radar signal out, and the radar profile looks like this blue thing. And what that means is across the axis is frequency, and so you have a narrow frequency range of light that you're bouncing off it. It's almost one single frequency, but it's a little more than that. And then you bounce it off it. Well, if Mercury is spinning, then some of it's going to bounce off the side that's spinning away from you, and some of it's going to bounce off the side that's spinning towards you. And that means they'll have different Doppler shifts. The one that's spinning away from you, the light that hits that will be red shifted, and so it'll come back with a longer wavelength. And the one that's coming towards you will be blue shifted. And so what happens is if your object is spinning, depending on how fast it's spinning, it can come back looking like this or like this. And it turns out you can figure out the rotation rate from how spread that original pulse is. If it's not spinning, of course, you just get the pulse back the way it went out. But if it is spinning, you get this kind of thing. And so they were able to deduce its rotation rate by looking at how the pulse came back. And that's how they figured out that it was taking 58 days to spin about on its axis. That D shouldn't be there. It should say Caloris Basin. This is this partially flooded impact basin is the largest known structural feature on Mercury. It was a massive collision that Mercury had towards the end of the cratering area. You can see that there aren't that many craters inside it, right? It's this big region here, right? There's more craters on the outside than on the inside. It's an area of almost 2 million square kilometers, so I don't know what that is, and it's about 500,000 square miles. It's a big area. There's a similar giant impact on the moon. All these giant impacts happened at the end of the cratering era, and that's not an accident because that's when the biggest objects were floating around. All right, eventually they ran into something. Mercury also has these things called scarps. If you look at this little ripple here that's going along the surface, notice it cuts across these craters, right? You can see it just cut right across craters. So that means it happened after the craters happened, almost certainly. And these are called scarps. And astronomers conclude that the compression that as the planet cooled, I don't know why it says planks like this in the Planck surface. Must have taken place after the craters were formed. It should say planet surface. So these ripples, you know how things will shrink as they cool. Well, that's what produced these ripples and these scarps in the surface. And I think they're half a mile high and 100 miles long or something. It has quite a few of them around the planet. These ripples that happen as a result of shrinking. And here's some questions.